All right, so the last video gave an introduction to the concepts for section 3.1. Now this video and the next video or two are going to go over examples. Now for this video, I'm going to focus on just finding critical numbers, and recall that if f prime of c equals 0, or f is not differentiable at c, or that basically means the derivative doesn't exist at c. So you could just say f prime of c doesn't exist, so D and E. Then x equals c is a critical number. All right, that's the definition, and why it's important is because finding the critical numbers allows us to find relative extrema. And relative extrema, that's just basically min or max values to the graph. So because at the critical numbers, that's generally where the relative extrema occur. And so if we're going to try to find the relative extrema, we need to first find the critical numbers. All right, so this video strictly just goes over how to find critical numbers. And I'll be working these three examples. All right, so to find the critical numbers, you first need to do is find its derivative. So find f prime of x. And then find the critical numbers themselves. You either set f prime of x equal to 0 and solve for x, or find any cases where f prime of x doesn't exist. I would say most of the time it's going to exist, and really you're just going to be setting f prime of x equal to 0. All right, so for number 17, f of x is equal to 4x squared minus 6x. So what we need to do is find the derivative. So f prime of x, again, it's 4x squared minus 6x. So we do 4 times the derivative of x squared. Derivative of x squared is 2x. So it'd be 4 times 2x based on power rule. And then minus 6x, the derivative of that is going to be minus 6 times 1, since the derivative of x is 1. So the first derivative is equal to 8x minus 6. All right, that's the first step. Now the second step is to find either cases where the derivative doesn't exist, or find the cases where f prime of x equals 0. So I'm going to say, note, this 8x minus 6, this is a polynomial, so f prime of x is a polynomial, so it exists at all points x. All right, so that's just a comment. I don't necessarily need to see that written on like a test or something. I'm just saying there's not going to be any cases where the derivative does not exist. So I only focus on finding x values where f prime of x equals 0. All right, so our f prime of x is 8x minus 6. So I set this equal to 0, and solve for x. All right, so we would add 6 to both sides, so you'd have 8x equal to 6. And then you would divide by 8. So then x is equal to 6 over 8, which you would reduce that to 3/4. So the critical number is 3/4. And they'll use the letter C for critical numbers, so I'm just going to say C equal to 3/4. Okay, and that's the answer. All right, and that's the general process that we go through to do these problems. We first find the derivative, and then we look at the derivative function and see if there's any x values for which it does not exist. Most of the time it's going to exist on some domain that they give you. And then you find x values for where the derivative equals 0. And those will give you the critical numbers. So these next two examples, you still go through the same thought process. It's just finding the derivative, and the algebra is what's going to be more complicated than this one that I just did. Okay, so make special note that they tell us the domain. So they already specify that t is going to be less than 3. Okay, so knowing that they specified that, we have to take this into consideration when we're finding its derivative. All right, so to do this problem, I'm going to be using product rule, and I'll write g of t so as the following. So instead of the square root of 4 minus t, I'm going to write it as t times, and then 4 minus t raised to the 1/2. And I have a product, so I'm going to use product rule. All right, so my function u is going to be t, and u prime is 1 since the derivative of t is 1. My function v is going to be the 4 minus t raised to the 1/2. And v prime, so I use the general power rule, which I guess I'll go ahead and just write that, which is really application of the chain rule. All right, that's the general power rule. So in our case, u would be like the 4 minus t. That means u prime would be 0 minus 1, which is -1. So u prime is -1 if I'm applying it with this. So based on the general power rule, the exponent gets dropped down in front, so it'd be 1/2 times 4 minus t, and I subtract 1 from it, so it'd be 1/2 minus 1 times u prime, And since u is 4 minus t, the derivative of 4 minus t is negative 1. Because derivative of 4 is 0 except a constant, and then derivative of minus t is minus 1, so it's 0 minus 1, which is negative 1. Okay, so I could write this as negative 1/2, and then I'll just leave the exponent negative for now. So 4 minus t to the negative 1/2. All right, that's v prime. This is u prime, u, and then v. So based on our power rule, g prime of t is going to equal u prime times v. U prime is 1, and then v is the 4 minus t raised to the 1/2. Then plus u, which is t, times v prime, which is the negative 1/2, 4 minus t to the negative 1/2. All right, and now this is the hard part, is doing the algebra to simplify it. Let's see, so what do we have? So g prime of t. So 1 times 4 minus t raised to the 1/2. I could go ahead and just write that as 4 minus t raised to the 1/2, which is the same thing as the square root 4 minus t. Then I'm going to have minus, and so that it'll be t divided by 2 times 4 minus t to the 1/2. All right, and because it was a negative 1/2, I brought it down to the denominator to make that positive 1/2. But we already know that raising something to the 1/2 is taking the square root. So I'm going to go ahead and just write it as the square root of 4 minus t on the denominator. All right, and this is all algebra, just to make it look more simple looking. And now I'm going to try to combine this into one fraction. All right, and really the only thing I need to do is multiply the first term top and bottom by square root of, 2 square root of 4 minus t. So I'll rewrite it. So square root of 4 minus t is the same thing as that over 1. I want the same denominator of 2 times square root of 4 minus t. So I would multiply this top and bottom by 2 times square root of 4 minus t. Then minus, and I'm just writing the second term over again. All right, so g prime of t. So I have square root of 4 minus t times square root of 4 minus t. That makes the square root go away. But keep in mind, I still have the 2 in front of it, so it'll be 2 times 4 minus t. And now they have the same denominator, so I'm going to go ahead and make it one fraction. So then I have minus t. All of that's divided by 2 times square root of 4 minus t. And then I distribute the 2. That makes that 8, and then minus 2t, but then I have this other negative t, so it becomes negative 3t. So it'll be 8 minus 3t over 2 square root of 4 minus t. And I would just keep it like that. You could rationalize if you want. I think here once it's one fraction, it becomes simple enough to find when it's going to be equal to 0. Now, I'll say a comment. We know if t was 4, then you'd have so these 2 times square root of 4 minus t, that's going to be 4 minus 4, which is 0. And the square root of 0 is 0, so you do 2 times 0, which is 0. So basically, you would have 0 in the denominator when t is 4. Which would mean it doesn't exist. But they tell us in the question that the domain is t less than 3. So we don't care about this value 4. All right, if they did not tell you a domain, you would have to take that, I would take that into consideration. All right, so now I'll drop it down here. So I need to find cases, find t, where g prime of t equals 0. All right, I don't care about the cases. The only case where g prime of t doesn't exist is t equals 4, but since the domain is specified to be t less than 3, I just ignore that fact. So I only focus on finding the values in which its derivative is 0. All right, so I find t where g prime of t, well, g prime of t is 8 minus 3t over 2 square root of 4 minus t. I need to find t that makes when this is 0. All right, and we've already talked about the only time you get the denominator to be 0 is when t is 4, but that's excluded from our domain. Now, if we want this to equal 0, the only time it can be equal to 0 is when we have 0 divided by some number in the denominator, where this number is not 0. And since the number in the denominator is not 0, it's only the number in the numerator that matters. All right, so really, I only focus on the 8 minus 3t. You could multiply both sides by 2 square root of 4 minus t and get to that same thing. And again, because for all other values in which t is not 4, and in which t is less than 3, it's going to exist. But the point is that it's not going to give you 0 in the denominator, which it doesn't matter what the number is in the denominator. It's just the fact that it's not 0. And so the number in the numerator is what counts, since we need 0 in the numerator in order for this fraction to equal 0. All right, so I find t when 8 minus 3t equals 0. So you'd subtract 8 from both sides, and you'd have negative 3t equal to negative 8. And then divide by negative 3. and then you have t is 8/3, and that's going to be the critical number. And again, they use the letter C for critical number. So the hard part was doing the algebra. You don't have to necessarily do all this algebra as long as you can determine when the derivative is 0, but I think it helps to simplify it as much as you can. And by that, just try to make it one fraction as one kind of term. But for that fraction, then you only focus on the numerator being 0 when its derivative is 0, since you can't divide by 0. So the denominator is almost irrelevant in a way, because it doesn't need to be, that can't be 0. So, but it doesn't matter what number it is for the denominator. It's just 0 divided by any number is 0 as long as the number is not 0 in the denominator. All right, so that's why we only focused on the 8 minus 3t, since it was in the numerator. All right, so that's that one. Next one's number 21. All right, they tell us also a domain for this one where 0 is less than x and less than 2 pi. All right, this is the domain that we're working with. So the steps, I find the derivative, I find when the derivative is equal to 0, or cases in which the derivative doesn't exist. Now for this, if I'm going to find the derivative of this, recall for derivative of sine of u, that's equal to cosine of u times u prime, and then also the general power rule. And then derivative of cosine is negative sine. All right, so for sine of squared of x, maybe it will help to write it as h of x equal to sine x raised to the second power. That way, you know you got to use the power rule, and then plus cosine x. So I find the derivative, h prime of x. So the operation of squaring something, that's using power rule. So I drop down the exponents, be 2 times sine of x raised to the 2 minus 1 times the derivative of sine x. Well, the derivative of sine x is cosine x. So it'll be times cosine x. All right, and then derivative of cosine is negative sine. So it'll be plus negative sine x. And so I use the general power rule for this, where our u portion is sine x. Derivative of sine is cosine, so that's where the u prime part is. So this is like u prime. And then we did the general power rule. All right, so now I'm just going to try to do some simplifying. So what do we have? We have h prime x equal to, that's really sine x cosine x. And then minus sine x. All right, and sine and cosine are continuous on any value x between 0 and 2 pi. So there's going to be no cases in which the derivative doesn't exist. And sine and cosine are continuous for all x where x is between 0 and 2 pi. So I only need to focus on finding the cases in which the derivative is 0. All right, so I'm setting the derivative equal to 0. So that's going to be 2 sine x cosine x minus sine x equal to 0. And I'm going to solve for x. Well, I can do some factoring. So I can factor out sine. And that's going to give me 2 cosine x minus 1, and then equals 0. And I have two factors. So the first factor is sine x. So case 1 is sine x equal to 0. Well, if you're looking at the unit circle, the cases in which sine is 0 are generally when x is like 0, pi, and 2 pi. But we don't include 0 and 2 pi because our domain is talking about x being greater than 0 and then x being less than 2 pi. We're not including 0 and 2 pi. So if they had 0 less than or equal to x, less than or equal to 2 pi, then we might consider it, but we still wouldn't just because we can't use endpoints for critical numbers. So that's another comment. So even if it was less than or equal to, we still wouldn't include it because we don't use the endpoints of an interval. For critical numbers. So we don't include 0 and don't include 2 pi when we're finding the critical numbers. All right, so that produces only pi for case 1. All right, now case 2. We set 2 cosine x minus 1 equal to 0. All right, I would add 1 to both sides. You have 2 cosine x equal to 1, and then divide by 2. So then you have cosine x equal to 1/2. And then you look at the unit circle and determine when is cosine 1/2. And cosine is 1/2 when x is pi over 3 and 5 pi over 3. All right, so combining these two together, the two cases together, we get there's 3 critical numbers. So since there's 3 of them, I'll let C1 be the smallest of the three, so that's pi over 3. And then C2 is going to be the next one in ascending order, so it would be pi. And then C3 is 5 pi over 3. So that's the three critical numbers. Okay, so that's going to be the answer. All right, so that's where I'll stop it for this video, and in the next video, I'll show examples of finding extrema on a closed interval, now that we've seen examples of finding critical numbers.